All right, lecture 30. We've only got a couple weeks left in this class, and we are surviving all of the changes that have happened to us. Boy, did I not expect to see this coming at the beginning of the semester. So let's talk about virtualization of systems. There's a number of different kinds of virtualization. We're going to talk about complete virtual systems, emulated systems, jails, containers. At a certain basic level, this is all about how to run an entire operating system as an environment inside another operating system. And there's lots of reasons for doing that. My first experience with this kind of stuff was working on a contract many, many years ago, and they wanted to have better performance. This was the United States Postal Service, and they had their software written for OS 360. Somebody can look up just how old that is, and realize that I've been doing this for a while, the gray hair and all. But yes, OS 360, and their solution to improving their performance when they bought new OS 370 systems was they had a thing called a virtual machine, and they brought up 6 OS 360 machines on their real hardware, their host system, which was OS 370, and they ran their existing software. And since they had 6 of them, it ran a lot better than one, and it was a lot faster, and they didn't have to rewrite everything. I guess the moral of that story is it's far easier to emulate and bring up stuff that already exists than it is to rewrite. So, I didn't think much about it at the time. I mean, it was a solution to a problem, and they brought it up and they ran it, and I was kind of like horrified that they wouldn't rewrite it and modernize it, because there were lots of reasons why OS 360 was absolutely just mind-bogglingly horrible. I went on to other things in life. So, most people didn't really experience a lot of virtual systems until the advent of a thing called BSD jails. BSD jails are a security virtualization that's not a complete operating system virtualization. Basically, you can put a process or a set of processes inside one of these jails, and they are completely contained. They don't have access to your entire operating system. They can only see the commands and the interfaces that you give them intentionally at the beginning, and they're locked up. And as a security isolation thing, it is awesome. Okay, the jails were eventually incorporated into Sun Solaris, and probably some of you at some point have actually used this and you didn't even know it. Yahoo runs their entire system on top of FreeBSD and uses jails for all of their processing, basically to enhance security. But it is not a full virtualization. It is, you are still running on FreeBSD or on BSD Unix or Solaris. What it is now the process that's running inside, like a web server or an application server, it can only see that set of files and things that it needs, and it can't see the whole operating system. It can't see, say, the password file and try to decrypt it, because the password file probably isn't inside the jail that it's running in. And this has all sorts of nice security implications. Lots of people that in the past sold access to systems where you could actually log in, this is the way that they did it. Is you logged in, but you didn't log into the actual system. You logged in inside a BSD jail. And they're very efficient. Since it is at the operating system, you're only losing about 0.5% performance compared to just running directly on the system. I mean, there is a little bit of overhead, but it's not very much, and you get a lot of security. Now, along with the BSD jails, there is a thing called chroot. Chroot is kind of the baby version of a jail. It was originally developed for taking and testing new operating systems, but let's say you're building some application and you're running on version 5.4 of the OS, but you really need to test it on 5.5. So you set up everything with the libraries, with all the stuff for 5.5, and you do this chroot. And inside your location where you're going to test, you tell it to replace everything that normally is the slash, the top of the tree, with this path down to your test1 directory. And suddenly your application sees everything like it's at the root, it's got all the files, it's seeing it, but it's replacing this root directory path with this other one. And that's how you can test across versions of stuff that otherwise you wouldn't test. Now, chroot is only file system oriented and doesn't provide complete isolation of all of your system calls, all of your things. Like if you're chrooted and you ask the operating system what processes it has, you see all the processes, not just the ones that are inside your little workspace. So it's not a complete container. Whereas jails in BSD, once you're inside the jail, you only see what's inside the jail. You don't see anything else outside. Now, if you did chroot and you didn't just do chroot, you combined it with a special file system mount and a different file system driver, and you had the ability to do a different kind of file system. Say one that when you installed stuff, instead of rewriting it, replaced it with pointers to the new stuff, but the old stuff was still there. The combination would give you pretty good isolation, but not complete isolation between what's inside and what's outside. And some people realize this and remember that this is way more efficient than a complete virtual machine. In a complete virtual machine, you've got 10-15% overhead. This is maybe 0.5% overhead. So you get a lot more of the machine, and it also doesn't take up as much space. When you do a complete virtual machine like VMbox or VMware or VirtualBox, those things, you have to install an entire operating system with all the space and all the overhead. So this way you don't have all that overhead. You just have this little subset. More efficiency, less space used. You could run a lot more things on it. It would be lower overhead. And it provides lots of capabilities of virtualization. So the virtualization stuff, they wanted it, but they didn't want to have the overhead. And some people created this system called Docker that provides that. Now, all of this virtualization stuff is built on top of some special instructions in the processor and virtual memory. Basically, these special instructions allow you to emulate the hardware layer completely so that you can build a complete virtual machine. And in combination, this has allowed us to virtualize all of these systems. So if you go back far enough, you'll find out that Intel's processor couldn't do this, and eventually they have these special instructions and it can. So they actually, at the hardware level, started supporting that. That is what allowed people to build these things and use them. There are a bunch of different software systems that do this. I think I mentioned VMware. I use that. Parallels is one that works for Macintoshes and does a very nice job. Usually in the land of Unix, you're looking at things like KVM, the kernel virtual module. Oracle bought Sun Corporation, and with it they got VirtualBox, which was a virtualization system. And they still give it away for free, sort of. And all of those guys are all full virtualization. Whereas there is another kind of virtualization that allows you to emulate, but it's not the same hardware. So you're not running the instructions natively, you're emulating every single instruction. The best examples of that are QEMU, which has been around for a number of years and does a wonderful job at emulation. And there's a fairly new one called Unicorn that allows you to build custom emulation systems instead of just emulate a particular kind of hardware. Now, QEMU has emulation, but since it is emulating every single instruction, it's a lot slower than these things like VirtualBox, where VirtualBox emulates everything, and every time you do some instruction that does I/O, that accesses a disk, a network card, it interrupts the guest OS, emulates the behavior of that particular piece of hardware, and then restarts the OS. So that most of the time when you're running stuff, it runs at near machine speed. Things like QEMU are much slower because they're emulating. They're doing what we did in the homework to emulate the actual hardware in software. But the advantage of these things is that these emulators can run a CPU that you don't have. For instance, I can run a MIPS version of FreeBSD on my Macintosh in QEMU. And there's a lot of application for that kind of emulation too. If you do mobile development, chances are you're not doing it on an ARM processor, which is what is in our phones and our Androids. And chances are you are not working with a touch screen the size of your mobile phone. So this emulation of the actual instructions is really useful for testing things you don't have, and also for doing things like automating testing. So collectively, this is the system level. Let's have hardware, but let's make fake hardware, and let's be able to test with it and run with it and build it. And there are times when each one of these has its own advantages. For instance, we're going to actually build a Docker container and run some stuff. It has the advantage of packaging up a piece of software and allowing you to have that software already set up, ready to run. You can transport it anywhere you have Docker, and you can run it. And that is a hugely advantageous thing, especially if it's a complex setup. On the other hand, sometimes it takes a long time to get a Docker container to build because it starts out with an empty container and installs everything from the OS up to the piece of software that you want to run. Last summer, I was doing some stuff where I needed to do a particular kind of compilation, and I started out with a Docker container, and I was noticing that this thing took a long time because I had to install a lot of pieces. And in fact, it was taking 20 or 30 minutes to build the Docker container to do the thing I was wanting to do. And I went out and downloaded a copy of Ubuntu, installed it on VirtualBox, and just logged in and just copied in the little file that I was wanting to compile, and compiled it and got the results, ran it, and copied it out in the amount of time it took to just build the Docker container. Not to run it, just to build it. So the fact that I could install this once and not have to redo it over and over again was tremendously advantageous. Another thing is that Docker runs on top of a custom file system. And that file system doesn't work the way that standard file systems work for a lot of reasons. That allows Docker to work the way it needs to work. But that custom file system is not conducive to running databases. So although Docker is useful in test for databases, it's not a useful production system for things like relational databases, MySQL or Postgres. You don't want to run a production Docker system. You want to run something like a virtual system or actually run it directly on hardware. So in any case, we'll go through a demo of how to do VirtualBox and install a system. You'll probably want to do this. This is a homework as well. But you'll want to do this for our next lecture, where we talk about process management and how processes work in a Unix system and how they're different than Windows. And we'll also run a little tiny demo of doing a Docker container and building a Docker container. And there are thousands of different Docker containers that are available for all kinds of different software. So instead of having to figure out all the details of how do I install this software and get it to work, I can just grab the Docker container, run it in Docker, and there's the piece of software. And I don't have to learn the installation and system setup for a particular piece of software, which is also very, very handy.